Hi everyone, this is just a reflection video for our POGIL, I believe it's POGIL 11. We call this one the microscopic view of electrochemistry. I'm also going to include a little additional content at the end of this video that talks about sort of shorthand notation for electrochemical cells. So you want to make sure you pay attention to that because we expect to be able to interpret those. So this POGIL, if you recall, was one that we did on Monday and Tuesday of was it the October 30th and October 28th. A little bit of that also on the previous Friday. The point of this was really to get you guys to start thinking about electrochemistry, since many of you have not seen it since college chemistry, and perhaps you haven't seen it at all to this point, depending on who taught your college chemistry course. And so it was a little bit of a refresher on that, but it also wanted to push you to think a little more about what's actually happening at the surfaces in an electrochemical reaction, because you'll see as we go further into this, into the electroanalytical techniques that we're going to learn about in this section, that electrochemical techniques are typically interfacial techniques, and that's both a strength and can be a weakness of the technique. And so it's important for you guys to start thinking at this microscopic level, because that's going to explain a lot of the phenomenon that we will study. Alright, so this is just a quick reflection, and as you recall, we spent a lot of time thinking about what was happening at the surface if you put a metal into a solution that contained the oxidized form of that ion. And so we sort of showed these before and after equilibrium processes, and we went through and we counted and we figured out how many electrons are moving in which way. And what we noticed in this case of this metal, when we counted them up, that there was more oxidation occurring, right, when you counted the number of ions here compared to there. So in general, it seemed like this zinc metal preferred to be in the oxidized form. And so we started thinking about it, we drew out pictures here, and you think about what's happening at the surface, because we remember as we convert, we're going to be having a transfer of electrons as we oxidize. We're going to have some reduction happening at the surface, but also going to have some oxidation occurring here. And so we need to think about where those electrons went to, and what we were discovering, something's funky is going on here. What we discovered was that, I don't know, having a little bit of an issue here. Alright, sorry about that snafu. What we discovered was that, we had to think about the sort of property of this metal. This metal, we think of it as sort of a, electron C, that there's basically a lot of delocalized electrons that are sort of in this metal. And so as these guys get oxidized, their electrons are essentially contributed to this electron C. And so when we thought about what was happening from a charge standpoint, we saw that the metal here was developing more negative charge here, and that conversely, just outside of the electrode, where you started developing a lot of these oxidized forms of the zinc, there ended up being a slight positive charge. So we put a slight positive here and a slight negative here. And then we compare that to the bulk solution. In the bulk solution, the charges are neutral. But here we have a situation where the positive charges here are attracted to the negative charge on the electrode. And so we end up forming what we call electrical double layer, which we call EDL, electrical double layer. And this is something we're going to see a lot, particularly when we get into potentiometry and when you think about things like ion selective electrodes and things like that. The most common ion selective electrode that you all are familiar with is a pH meter, and that is going to operate a lot under these principles, because this understanding this electrical double layer is going to tell you about the potential that you're seeing. And we compared a couple different situations. We compared zinc to lead, and what we found was, just from these little cartoon pictures here, we saw that both of the lead and the zinc were more likely to be found in the oxidized form than they were in the reduced form, but that the zinc, the relative amount of this favorability for oxidation was stronger for zinc than it was for lead. And you saw how that affected the electrical double layer, that we ended up seeing electrical double layer extended deeper into the solution for the zinc than does for the lead, and that's exactly what you'd expect to find under these situations. And so we talked a little bit about standard reduction potentials, which we called E0. What we found was that E0 for zinc equaled, what was that, negative 0.763, and these are in volts, and the E0 for lead, right, this is just a piece of information we can find on a table, was negative 0.126 volts. And what we sort of said was that essentially, so this is a standard reduction potential. So this told you something about that metal, how much that metal wanted to be reduced. Okay, and the larger this value is, the more positive value this is, the more likely it's going to be reduced. And we saw because both these values are negative, that means that they both would prefer to be in the oxidized forms under standard conditions. But you can see from the magnitude of this that because the zinc magnitude is far more negative than the lead value, that this wants to be reduced even less than this, right? This wants to be, and so conversely, you need to think about these things as sort of two sides of a coin. Every time there's oxidation, there's a reduction, and the more likely something is to be oxidized, the less likely it is to be reduced. And so this is more likely to be oxidized than this, okay? And so it's important to sort of think about those things and to be able to sort of experiment, with that logic. And we talked a little bit about the thermodynamics and the equilibrium and how this all relates together. And hopefully that all made sense to you guys. Again, you can go back to chapter 13 and review if you'd like to see more of this. And you guys are going to see when I assign some problems tomorrow and Friday in class. That would be November 1st. That would be due next week. Then again, that's going to be in place of your quiz. Those questions will relate to some of the things from this class, and so a lot of the reading from chapter 13. So please take a look at that. So I want to talk about this thing called shorthand notation, and maybe let me insert the next slide here. Just one second. There we go. Let's go here. Okay. No, slideshow. Come on. Resume session. All right. So. Shorthand notation. There's a couple things I want you to see. So we're talking about galvanic cells, and that's what we began with POGIL 13, and we're going to continue that for the next couple days. And you'll see a funny way that people write things, and this will make more sense when I show this in a second. And that is to try to represent the galvanic cell, which is something that looks like this, right? Instead of having to draw out that whole picture showing what this is, that we want to set it up in a different way that you can understand it in a real shorthand notation. So there's a couple things that you guys need to realize, and one of them is that we're going to see these vertical dashes. And this line, if there's a single one, that represents a phase boundary. Phase boundary. Okay. And if there's a double line like this, that represents a salt bridge. Okay. So it's important to really understand how those operate, and that phase boundary means that you have two different phases in contact with each other. So you might have a solid in contact with a liquid, or two liquids. Well, I guess you have two liquids unless they're immiscible, but you could have a gas in contact with a liquid. You could have anything like that. I guess another thing, but there's going to be an example where we see a liquid in contact with another liquid, and you'll see that in a few minutes. And a salt bridge is an important thing that we said, and you guys have explored this a little bit in POGIL 13, and that's a way that we can maintain electrical contact, so you can complete a circuit, but without actual mixing of the solutions. And so this is a galvanic cell, and I also want to make something important notice here, that by convention, right, we always put the positive terminal here on the right. Okay, you see this is set up to a voltmeter. And this one on the right, which we designate with a positive, is the cathode. All right, and the way I think of this, if you guys remember from cations and anions, you recall that cations are positively charged, and so I think of, okay, cathode positive, it's a positive terminal. Okay, and the one on the negative side, now we always put this on the left. I'm going to write this on the right. Right, this is by convention, and it's the way we always do this. And on the left, this is called the anode. If I spelled that right. I forget if there's two N's in that or not. But again, just like the cathode, you can think of cation, think of positive charge. Anode, think of anion, think of negative charge. And that always goes on the left. Okay, so that's convention. And that's going to be important because, as I said, the direction, the magnitude, whether something is positive or negative, is going to depend on which which direction these things are hooked up. And so it's important that we keep things consistent and always set things up in the right way. So always set up the cathode, the positive terminal on the right, and the anode, the negative terminal on the left. Okay, so I'm going to talk about this transition. So the way this works is on one end, on the left end, we're going to start with the cathode, or so, excuse me, the anode. We're going to start just like this thing is set up. We're going to start from the left and move to right. And so if I was trying to draw this, I would say, okay, on the left, at the anode, you have a metal, and that metal is cadmium. So I'm going to write cadmium. This is a solid, right? This is a metal. And so you have to ask yourself, what is this in contact with? So you see this cadmium metal is in contact with a liquid solution. And you see this is a solid, and it's in contact with a liquid. So because of a solid-liquid boundary here, that is a phase boundary. So if you remember from what I showed you before, we're going to draw a single vertical line here, and that gives us a phase boundary. And then what is this in contact with? It's in contact with a solution of cadmium nitrate, which is in aqueous solution. And so this is, we write in that right here, cadmium nitrate. Sorry, this is getting, writing this a little cockeyed here. Okay. All right, now if you keep moving left to right, and we see that this, at the right here, the next contact here is a salt bridge. All right, and so if you remember from our previously, salt bridge is 2 lines. Okay, so that's what that looks like. And then what's that salt bridge connected to? It's connected to another solution. In this case, this is silver nitrate. And this is an aqueous solution, so you write silver nitrate. All right, this is also aqueous. And then, again, now this is in contact with the cathode, which is a solid silver metal. And you're done. Okay, so this is how we would write this out in shorthand notation. It's important to know that, again, that this is your anode here, so this would be the negative terminal, so you can think of it that way, and your positive terminal is here. And this is going to be important because at some point we're going to be calculating these cell potentials, and so you need to make sure you keep these straight. And you're always putting the cathode on the right and the anode on the left. Alright, so that's how you would draw out. So you'd be expected to be able to know how to do this. If you see a solution like this, to be able to represent it in the shorthand. But more importantly, you need to be able to do the reverse. And that's to start with one of these and then picture what it looks like. Okay, because that's when it comes to calculating, figuring out your cell potentials, that's what you want to do. So we're going to do that here now. And so this one is more complicated than that last one. And so it's going to be a little trickier, okay? And so what we're going to see here is, this is going to be a real test of my drawing skills, all right? And so I'm going to set this up. You know, generally we're always going to have a couple of beakers, okay? It's one beaker. And then we're going to have another beaker, okay? I'm going to draw that over here. And we're going to have these two things connected by, in this case, we're going to use a voltmeter. Right, so let's put a V here. All right, now I'm going to try and draw out the rest of these beakers without being too messy. All right, so there's one, and here's the other. All right, beautiful. All right, and so now I'm going to draw the other things in green here. And so let's see, I'll start with this. Let's say, okay, so we're going to start at the anode here, which is going to be a platinum wire. And this is going to be metal. So I'm just going to draw this guy here. Say this is our platinum electrode. I'm going to draw an arrow here that tells us that this is our platinum, which is this right here. And this is going to connect to our voltmeter. And this is our negative terminal. Okay. So this is where it gets a little dicey here, because now what we're doing is we're moving into a solution that has some hydrogen being bubbled into it, right? So we have a gas in this case, and so I'm going to draw this in a different color so we can keep everything straight. And so now we've got, let's say, purple. So we're going to have a little, you can't really see where this is coming from, but this is going to be a little tube here, which is bubbling some hydrogen gas. Right, and we'll call this H2. Right? That's flowing through the bubble. All right, so that's in contact here. And this is a phase boundary between a solid and our gas. Now this is a little tricky because what we're actually going to have here is this is going to be in contact with solution, right? Because we need to have some sort of electrical contact. So this whole thing is going to end up being in water. And so, so that's essentially, right, there's this phase boundary here, right? And so we've done this purple one here. And so what we see is there's a salt bridge, right? That's the next step. We're moving left to right. We have a salt bridge, so I'm going to draw that. I might run out of colors here, but we'll see. I'm going to draw that in yellow. So here's our salt bridge. Beautiful, beautiful yellow salt bridge. Feel like it's a happy little salt bridge. Okay, and so now, right, so this is just an aqueous solution here. I'm going to give that blue, right, so we're just in an aqueous solution, right, and this is where our salt bridge is. Alright, so this is where things get a little interesting. Alright, so now we're dealing with an aqueous solution that has two compounds in it here. Like, see that? Because there's a comma here, and there's no phase boundary between these two, so these are both in the same solution. Alright, and so what I'm going to do is I'm going to draw, I guess I'll use the blue here. Alright, and so I'm going to say that inside this is, we have two solutions. We're going to have our mercury complex with EDTA, our old friend. We see that we're told that this is at 0.0050 molar, so somebody's doing some sort of EDTA titration here, and we have free EDTA at 0.0150 molar. Okay. Now things are a little interesting, because what we see is we have another phase boundary here, right? So I'm just going to sort of say this is that whole blue section I just wrote. We have another phase boundary, and this phase boundary is with a liquid. And that is what's in contact with our cathode. So let's draw that out. What's a nice color we can use for this? How about orange? That sounds fun. All right. So here's our orange. All right. And so I'm going to say this is, right, this is a liquid boundary. So note the salt bridge is in contact with the mercury solution, but is not in contact with this other one here. Right. And this is a liquid. And this, we're going to say, is our mercury liquid. Right, so this is what I was talking about before, where we actually have two solutions in contact with each other, two liquids in contact with each other, but they're immiscible. And so that's why we have a phase boundary between these two. So that's our mercury. And finally, our cathode is a platinum wire. And so this is a little tricky, because we don't want to have our cathode in contact with our solution here, right? Our cathode, by the way, is set up is in contact with the mercury. And the reason I've drawn it like this is because we know that mercury is more dense than water, and so that's why it's on the bottom. Boy, I'm out of colors. I'm going to give it a, oh, I'll try white. Let's see how that looks. All right, looks not so bad. All right, so there we go. So we just draw it and we say, all right, our platinum wire is in contact with our mercury. And there we go. Bam. Alright, and so that's how that looks, right? It's kind of a lot of colors there. And this one is a little more complicated than I will probably ask you guys to do, but I'm going to give you some practice problems. I may give you one of these on your quiz to work on. So take a look at this and give it a shot on your own. And I'll see you all in class tomorrow.